sodium chloride, Na plus, Cl minus. They're separated now, but if the ions come together, because opposites attract, they form straight lines. And this is called a lattice. We have a negative and a positive and a negative lined up into a beautiful crystal structure. Here goes the hot snap. Watch the crystals form. Oh, that feels so warm. Good on a day like today. Today's lesson is all about ionization energy, the amount of energy that's given off when two ions come together. We'll look at a couple of examples. We'll talk about what causes these ions to be attracted to one another and form a lattice. And then we'll do some calculations using our old favorite formula, M times C times delta T. Mass times specific heat times the change in temperature. And then last but not least, we'll calculate the amount of heat given off per mole of substance. Well, the first thing you might be asking yourself is, now what the heck is a lattice anyway? And so what I have here is a picture of a lattice fence, like you could buy at Menards or some Home Depot or someplace like that. Why do ions form lattices? And they do that to minimize their energy. This is an answer that you've seen before, right? Things like to have low energy. And there are attractive and repulsive forces that are at work here. If you look down here, there's negatively charged things and positively charged things. And these ions love one another. But the negatively charged ions, like these two green ones down here, they both have a negative charge. They don't like one another. They repel. So, after these ions all settle in next to one another and they kind of shuffle around a little bit, there will be a particular distance between these ions, rather like the distances that we calculated with covalently bonded atoms. And they also make interesting patterns of arrangement that we'll look at later on. So what is the definition of lattice energy? Lattice energy is the amount of energy released when crystals are formed. An example is NaCl, sodium chloride. When these ions come together, they give off 787 kilojoules of energy per mole. So 6.02 times 10 to the 23rd particles of Na plus and Cl minus coming together gives off this much energy, and it feels hot. Lattice energy calculations. So let's try this. A lab is done in which 45 grams of an ionic substance forms a crystal lattice. The process gives off enough energy to raise the temperature from 45 degrees to 65 degrees Celsius. What that means is this. If you look over here at this apparatus, we have 45 grams of substance in the bottom of this, but it's not ionized yet. All the ions are just floating around randomly. And we're going to make them ionize. And when they ionize and form a lattice, then they're going to give off heat. And we will check what the temperature change is by looking at our thermometer and saying, in this case, the temperature starts at 45 degrees and it goes up to 65. So it starts at 45 and ends up here somewhere at 65 degrees. So our delta T is going to be 20 degrees. Our delta T, our change in temperature, is 20 degrees. Okay, so let's take a look at what we need to know. The specific heat of this compound is 3.4 joules per gram degree Celsius. Now you might recall that water had a specific heat of 1 calorie per gram degree Celsius. That means that if we're going to heat up 1 gram of water by 1 degree, it takes 1 calorie. And we also use the number 4.18, and that is the joules that it takes to heat up 1 gram of water by 1 degree Celsius. We don't need that now because we're using a different substance that is a little bit not quite as good of an insulator as water. This stuff heats up at a rate of 3.4 joules per gram degree Celsius. Well, we're going to calculate the heat, which is given the letter Q as its symbol, which is kind of odd. But Q, or heat, is equal to M times C times delta T. The mass, in this case, is 45 grams, times C, which is the specific heat, which is 3.4 for this substance, and the delta T, the change in temperature, which in this case is 20 degrees because it goes from 45 to 65 degrees. And then when we get down to part 3 here, we will deal with these two topics, which has to do with moles. So the first thing we want to do is calculate the total amount of energy given off in this case. How much energy is given off when this happens? So we'll use our MC delta T equation, M times C times delta T. All right, so the mass is 45 grams of substance in the test tube times C, and now this you look up in the back of your book, there's a table that tells you this, 3.4 joules per gram degree Celsius times the change in temperature, which is 20 degrees Celsius. All right, when we do this, when we multiply these together, we'll get a number right here. And the units for this are, well, let's figure out what the units are. Grams is on the top, grams is on the bottom here. When you multiply them, they cancel. Degrees Celsius is on the top here. Degrees Celsius, oops, forgot the degree sign, there it is on the bottom here, so they cancel. So the only thing that survives is joules. So our answer will be in joules. All right, let's multiply 45 times 3.4 times 20. All right, here we go. 45 times 3.4 times 20 degrees, and that equals 3060. Okay, 3060 joules. But, which is great, we have the answer to this this part of the problem. But we, if you have this number, you don't know if that amount of energy comes from a little tiny bit of the stuff or a whole lot of the stuff. So we want to figure out how many joules per gram, just like we did with our Cheeto experiment. So let's go down here and calculate the joules per gram. Well, the first thing is, what does per mean? It means divide. So we want to get the joules, 3060 joules, and divide by the grams of the substance. And that was 45 grams is inside the test tube. So we divide by 45 grams. Oops, I should have put that down here, sorry. And let's conjure up our calculator and take 3060 and divide by 45. And our answer ends up being 68. 68 joules per gram. So nothing cancels there, so we keep them both, joules per gram. Good. That's how much energy 1 gram of this substance gives off. And a lot of chemistry is about energy, as you will find out. Now what we want to do next is figure out how many joules per mole. So we want to take 68 joules per mole, and we want to convert that to, I'm sorry, that was joules per gram. We want to convert it to joules per mole. We have joules per gram right now. My apologies. This should, let me erase this. Okay. Joules per gram. So we want to get a conversion factor and get rid of grams. And we want to get moles. Now, grams to moles information. If you think way back to about October, we were working on this kind of problem. Now, what is the substance up here? What's its molar mass? The substance is NaCO2. And so what's its molar mass? We need to figure that out. How many grams per mole? Now, sodium weighs 23 grams per mole. I got that from the periodic table. And we want to add the mass of carbon. That's 12. And then we want to add the mass of 2 oxygen atoms. So that's 16 plus 16. So 23 plus 12 is 35. Plus 32 is 67, I think. 67 grams per mole. Per how many moles? Per 1 mole. 67 grams per mole. So 67 grams per 1 mole. Now let's see what cancels. Grams on the bottom, it cancels with grams. Joules doesn't cancel, moles doesn't cancel. We'll take 68 times 67 divided by 1. 68 times 67 divided by 1 equals 4556. 4,4,5,5,6 joules per mole. Now, I should probably round this off properly, but we haven't really learned how to do that just yet. So that's our final answer. If you had a mole of this substance and you put it in a test tube, a pile of this stuff, you should get 4,556 or so joules of energy from this compound.